Welcome to Silicon Economics. Silicon Economics is a podcast where we explore the intersection of technology and economics. I'm Rob Soderberry, Executive Vice President and General Manager of the Flash business here at Western Digital. With me is my co-host,
Adarsh Kannan, VP of Economics and Data Science here at Western Digital.
Adarsh and I are excited to bring you this episode. Let's jump in. Well, hello. Today I'm thrilled to welcome Ravi Poddar. Ravi, welcome.
Thanks. Great to be here.
Ravi comes with serious street cred in the world of ASIC engineering, CAD, EDA. He and I share a number of things. One is an uncomfortable long time that we spent in the industry, bordering on the 3X era, bordering on the 30s of years. But very seriously, I'm excited about this conversation because we're starting to put the silicon in silicon economics. Actually, the first episode we've talked hardcore silicon. Now I know that you got your start with a PhD from Georgia Tech.
Yes, I did.
So, I've been affiliated with Caltech Engineering and Applied Science, and it was much to our chagrin that Georgia Tech moved ahead of Caltech on the top electrical engineering school ranking. So, my guys tell me that's purely because of size, but we're very, very much kindred spirits. And tell us about some of the other things you've done in your career, just by way of introduction to the episode here.
Yeah. Thanks, Rob. And so great to be here again. Done a lot of things. I think I basically started out as, went to Georgia Tech, got my degrees from there. And I started working at a chip company in Atlanta called Integrated Device Technology. Ever since it actually got acquired recently by Renesas. Oh. Maybe not so recent, but yeah, it happened. And I moved out to California to join this company called Transmeta. Right, this is probably ancient history, and many of your readers or listeners may not remember this company. But there was an article I remember reading in IEEE Spectrum about Transmeta going up against Intel, right? So who would go up against Intel? And they had this really interesting technology. But the really cool part was Linus Torvalds used to work there.
Oh, nice.
Yes. And I was thinking to myself, if Linus works there, this has got to be a great place. And so I literally put it in my resume, through the Cold system. I didn't know anyone in California, period. And I got a call back, for a CAD engineer role. So I interviewed for a CAD engineer role. And I came here and I interviewed, and they offered me management of the entire team. And so, I couldn't really say no to that. And I packed my bags and flew over to California, started at Transmeta. And I was there for about 7 years, through IPO happened, and then Transmeta had a very interesting history. I actually worked with Linus directly on a project, and he shook my hand, and I was like, I'm not going to wash my hand now for a week. I always say that was like one of the highlights of my career. So anyway, I was at Transmeta, worked on a lot of different things, including we worked with Sony on the cell processor at one time as well. And that's, so I tell my kids, that's the chip in there in the PlayStation 3. I worked on that, right? Mm-hmm. So, which is pretty cool. But after Transmeta, I actually went back to IDT for a short stint. And then, I tried to see what else is happening, what else is going around where I can use my expertise. And I saw this job description at NetApp. And I first thought, well, NetApp doesn't design chips, or I don't think they design chips. And so I put in my resume for this interesting job at NetApp, which required a lot of EDA experience. And lo and behold, about 3 weeks later, I was working there. And it was basically all about storage for semiconductor design, right? And how do you optimize storage, or can you optimize storage to improve the process of chip design? And so I got involved there, and we actually did some research with Synopsys to begin with about accelerate. Well, what I thought is, let's pick VCS at Synopsys as a tool to accelerate, because, it's so heavily deployed out there. And so we actually asked the GM of VCS at the time, hey, does storage impact throughput of your EDA tools like VCS? And I guess they were going through that exact problem with a customer, and they said, heck yes. And so we asked if they would partner with us to optimize storage for tools like VCS, and they said absolutely. So we got a bunch of licenses. We worked with their IT team and their engineering team, and we figured out some optimizations. And lo and behold, we actually published a paper showing that you could speed up VCS by 27% just by optimizing the storage layer, right? And I think that was a pretty big turning point for both NetApp and I think also Synopsys. Synopsys actually asked us to go to every one of their snugs and talk about this, which we did. And so I did that for a while. We optimized. Basically, we opened up this idea of, can you optimize a complex, highly concurrent application by optimizing the storage layer? And it was true in many, many cases. And so we did that for a number of things. And shortly thereafter, I left and went to this place called Pure Storage, because having learned about storage at NetApp, I was trying to understand, so what can be done now that we've learned that storage is kind of this limited to performance? Is there some new technology out there that can work on this and improve it? And Pure Storage had, or purportedly had, that technology, at least what they told me. And so I joined them very early on, and we released FlashBlade.
That worked out pretty well.
Yeah, it was pretty cool.
Yeah.
It was pretty cool. Yeah, absolutely. And the all-flash technology. It was interesting, the various things they did. We actually were able to get it into many, many customers who were running chip design at the time. And it's still pretty popular today. I left them about 3 years ago to join AWS because they had this interesting role, another interesting role which came up, which was called the Principal Semiconductor Industry Advisor. And so I applied for that one, and here I am.
Yeah, and so let's just sort of pause for
Yeah.
a moment and talk about AWS itself. So this year celebrated the $100 billion
Yes.
revenue run rate.
Yes, quite remarkable. And I think what's even more remarkable, and I don't know if I'm going to tell you exactly the right numbers, but I believe our CEO said at one point that only 10% of workloads are running in the cloud today. Right?
So it's another 10x.
Who knows, right? But that sounds like the pretty big market opportunity. And in the age of AI, I think that's gone up even further.
I think a lot of the viewers and listeners probably wouldn't realize the importance of AWS in making something that's important to them happen on a daily basis.
Right.
Every time you turn on Netflix, that's actually something that is happening on AWS with a very complex infrastructure delivering that content.
Yes.
And we're very proud to be part of the value chain where each one of those pieces in that stack, as you put it, requires intense engineering, right? And I guess now it's all going all the way down to the semi and making that customized.
No, absolutely correct. I think the level of, it's actually a common interview question these days is design Netflix for us, right? I think you've heard this
Right.
at Meta, Google, Amazon,
Right.
all these different places. So conceptually, I think it's not that difficult to understand as to how it actually works. But, I think I'm pretty sure so many products were created and enhanced to make this thing work at scale, because I think that's the real kicker, right? Because how do you make this thing work for, I don't know how many concurrent Netflix users there are. I'm sure it's in the tens of millions at any one time.
Right. And the
Yeah.
general purpose computer, when you sort of, take that paradigm, you had to adjust it for AI and have special purpose computer.
Right.
But the same thing for storage was not as explored, but definitely applications like Netflix and in your particular case, EDA applications have, benefited from thinking about specialized storage.
Absolutely. And I think that's another area which AWS has actually been investing a lot in, is the storage layer. And some of your customers, well, not customers, but your listeners may know that we have this framework called the FSX framework, right, which is essentially a file-based framework in which you can plug in different operating systems. That's a way to think about it. And so they have FSX Lustre, FSX ZFS, and also FSX ONTAP with NetApp. And especially in the EDA space or the chip design space, the NetApp one is really taking off quite well.
Well, I want to get into the ASIC stuff in a minute,
Yeah.
but since we're on storage and accelerating storage, why don't we pause there for a moment? It felt like until early this past year, early 2024, AI was this GPU conversation.
Right.
And all of a sudden, AI has become a storage conversation. And I would think with your understanding the stack, you have some insights as to why that's happened.
Yeah, I mean, great point. I mean, AI, generative AI, LLMs, what's the one thing that makes them great? It's data, right? And so the more data you have, the better it goes. And in order to train, these very expensive GPUs are needed, but you have to keep them fed, right? I remember me and a friend of mine, we coined this phrase, feeding the beast, right, a while ago. So how do you feed that beast while keeping costs relatively low? And so therefore storage, high performance storage, high capacity storage is becoming even more important, as you mentioned. Right?
Yeah, and one thing I don't think people realize who haven't looked at it is, while it is important to have SSDs that go with the GPUs and the GPU complex itself, ahead of that big GPU complex, you have a giant fast data lake,
right.
And you're doing all of this data preparation and embedding and vectorization, and all of that is really consuming an enormous amount of capacity and storage in the world today.
Yeah, it's like if you build a big mall and then you kind of, have like a really small entrance to the mall, you're not going to have as much sales happen.
Right.
So the real thing that you want to do is open up the gates, and the key role that I guess storage plays is enabling these GPUs to feed the beast.
Yeah, exactly. So I think that's an area that is constantly being looked at and optimized. And I think one of the actually, from the storage level, it depends on what it is that you're training, right? What is your model trying to look at? Are you looking at small data sets, big data sets, small files, big files? And actually different storage is required for each one of those modalities, you could say, right? So if you're looking at training on videos, you need extremely high bandwidth to your GPUs. And so storage systems like Lustre do really well there, right? But if you're trying to train on, say, text messages, those are very small files, and so Lustre may not be the best choice. Then you have to look at other things.
Yeah, so recently I kind of saw this video on trying to sort of explain the analogy between CPU and a GPU. So they try to paint the Mona Lisa. The Mythbusters actually get involved in this. And the CPU goes, each dot or pixel at a time, one by one, row by row. And then they show how the GPU would perform, which is essentially one shot on all the pixels. Can you maybe give us a little bit of an analogy there, Ravi, on how the storage equivalent would be, just so that viewers and listeners can wrap their heads around why this is a very different choke point?
Yeah, I think one way to perhaps look at it is similar to what you said, like one door versus a small door going into a big mall. In this case, I think of pipes, right? You think of small pipes versus huge pipes. And if you think of a pipe, you can think of lots of individual streams in that pipe, right? If your pipe is small, it'll feed one or two streams. But if you have a big wide pipe, you can feed many, many streams. And so then you can think of who is the consumer of that stream. And in this case, it's a GPU, right? And so if you could have more streams of data going to more GPUs at the same time, you can do much more efficient processing.
Right. And asset monetization economics is very straightforward there, right?
Absolutely.
You invest $1 million. The more those assets are sitting there unmonetized, which is they're not working, that's a problem.
Absolutely true. And in the cloud context, it's even more important because cloud bills per minute.
Correct.
Right.
Yeah.
So if you have unutilized assets or assets with low CPU, or if you look at the I/O weight going up, those assets are essentially, you're paying for assets which you're not really using. And therefore, you have to really optimize that layer.
Now, what your role is today at AWS, as I understand it, is really working with people like us.
Yes.
We happen to be both a supplier to and a consumer of AWS, as I'm sure many of our peers are in the industry. But it's working with people like us to sort out how to use cloud and AI in the ASIC flow.
Yeah, that's absolutely true. I do work a lot with cloud and customers who are trying to migrate workloads into AWS. And a lot of those customers are just trying to migrate EDA or chip development. Mm-hmm. For those who don't know, EDA is short for electronic design automation, which essentially is CAD software, the CAD flow for developing chips. And traditionally, those have been heavily on premises. But what we work with customers on is finding those workloads that are not getting enough compute on-prem and see if you can use the massive scale of the cloud to accelerate. One of our big customers doing that today is ARM. That's a great public reference for us. They're running at scales of hundreds of thousands of cores in AWS to accelerate the verification flows, to be able to do more chips in the same schedule. I think they recently, well, not recently, maybe last year, they talked about at our AWS reInvent conference that they're able to do like something like 40 or 50% more projects in the same time frame using the scale of cloud.
Yeah, and for a lot of people who are not familiar with the semiconductor industry, they may not like sort of appreciate enough the importance of the design to fabrication flow. It's like, for me at least, having come from a software engineering background, it took me a few iterations to sort of get it into me. This is a measure N, cut once business. The more you can sort of automate that measurement mechanism and make sure that everything seems in order, you're going to save a lot of capital, and you put your capital to better use downstream, right? Like, because once you go to the fabrication process, it's print.
Yeah.
And at that point in time, you want to make sure that the premise of what you've designed is giving you the yields, it's giving you the right sort of characteristics, and it meets the specifications. And so the EDA is huge in terms of making sure that the success of these downstream businesses happen. And ARM is a great example where they don't have any fabs of their own, but just by the virtue of being able to create really good designs, they have a successful business model that operates on it.
Oh, absolutely spot on, right? So I think chip design, if a big part of chip design economics or some silicon economics is first time right. Or first time rightish, right? With the idea that you can then fix it in metal if you have to, right? So, and how do you get there, right? You get there by pre-silicon verification, which is then run on these huge compute grids. And so the idea is you simulate as much as possible every corner case that you can. And the joy of this is silicon design is an NP-complete problem, right? So you cannot verify enough because of the complexity of these multi-billion transistor designs before you tape out. And so one of the big jobs of the design leadership team is watching that bug rate, right? And the bug rate gets down to where you think, hey, I think I'm okay.
Right.
Let's tape this thing out. And then you stuff your design with what's called spare gates. You stuff your design with, I can fix this in metal 7, metal 8, whatever, so I can catch the design as it's going through the process and change a mask. But yeah, I mean, it's all about getting that silicon right in the computer before you tape out.
So where is the industry in this movement of the EDA tool set to the cloud? Are we 1% in? Are we 10% in? Are we 50% in?
You know, what's interesting is it varies a lot by customer, right? So on average, I don't think I have a full correct answer for you, but my guess is it's in the 5 to 15% range, right, in terms of actual migration to cloud. But there are customers who are almost fully migrated already, and there are some customers who aren't migrated at all, right? So there is a continuum, and it also varies by what they're doing in the cloud. So for example, there may be some customer who just wants to run backend, which is actually the chip or the chip physical creation in the cloud. Right. Some customers only want to run front end, which is just the simulation, which they can do at huge scale. And there are some customers doing it all, right? There is customers like one of our good customers is Astera Labs. They recently went IPO, and they're a public reference for us. Right. They're everything in AWS, right, front to back. So it does vary quite a bit. But I see a huge trend of customers wanting to move, partially driven by complexity, right? So do you ever hear about chip getting smaller?
This is actually quite an interesting topic, because if you think about something like DNA sequencing, right? Like, it gave cloud providers a little bit of a wake-up call, because the way the cloud was provisioning the data ingestion, you couldn't use the network bandwidth to bring all the data that you do from sequencing on board. Right. So then, AWS had to think about solutions like Snowball, Tarball, like, one of those either those trucks that come and get parked in your sequencing lab, or you get like the suitcase that has a storage solution. So to the EDA world, it seems like there are obvious choke points that's kind of preventing. I'm curious to see what are some of those, and how is AWS moving to remove that bottleneck? Yeah,
another great question. So I think if you look at the tools themselves, right, made by the major tool providers, I would say all the tools work, right? EDA works, the flow works on AWS. So what was previously a technical challenge, I don't think that is there anymore. That's moved on. So the challenges we see mostly are related to concerns about IP security, which again, we have 3-letter agencies running in AWS. So I don't think
we're getting past that. I think in the
we're
cloud.
getting past that. Exactly, right? And so AWS also has a lot of hardware and systems and actually specialty chips which they have built to improve security. It's one of the things that's called our Nitro subsystem. You can look into that, which further enhance that. And actually, so I think Nitro is something they install in every server that goes into AWS. So the issues are mainly around security concerns, which are somewhat mitigated, and cost, right? Because it does cost money to run in AWS, and it's a different model than people are used to. Because they're mostly on premises today. So you're moving from CapEx to OpEx, and so there's some concern about how do they manage those costs.
And is the nature of the workload such that I get an ROI from that? Am I bursty? What's going to be my utilization of this infrastructure? How do people think through what that ROI equation is going to look like?
Yeah, another great point. So I think basically what customers do, or people who are investigating this do, is they first try to migrate those workloads which will guarantee consumption, right? Because there are many different economic models to use the cloud. One of the most economic ones is you commit to a certain amount of capacity, right? And often that capacity is built to order, right? Because
these are reserved instances.
But some of them are even special reserved instances.
Yeah, right.
Specially reserved because they may require special types of compute, which may not be popular for other industries, but if a customer wants them, they will almost build to suit, right? And so there are those kind of models. Then there's also a very interesting model which we have around what's called spot compute. And spot compute is heavily discounted, say 70, 80, 90% off list prices. But what spot compute is, for those who do not know it, it's the leftover compute in AWS, right? AWS has a lot of compute, and a lot of it is used by Amazon.com, right? For example, Prime Day comes along, Christmas shopping comes along. And that's actually, by the way, how AWS got started, because of all the leftover compute. And so that's available at high discounts. But there are things around it which make it, you have to be very judicious about how you use it. But some customers, I think ARM is one of them, they have figured out how to use spot compute very efficiently, right? And thereby they can run at these huge scales at low cost. But that being said, there's also new technology coming out by software providers that let you use Spot in a very efficient and predictable way, such that they allow you to move workloads from spot to spot to spot to spot and get job completion.
Yeah, this is actually a beauty of running a massive scale operation, right? You'll have to kind of provision to the peak,
right?
And like even if you provision to the peak and drive a lot of the asset utilization, you're still going to have that gap at the top in terms of the available compute to what you can fill up. Partly because you have to build redundancy into the systems itself.
That's right.
And so spot compute or evictable compute is there to stay, where you would have to kind of design systems that are redundant, but that redundancy may not be used all the time, which means you'll have to provision that layer. And to economists, the beauty there is that it's essentially a place where the capex for that asset in theory is zero, because whether you want it or not, you're going to provision that asset. So it's all about how much peak load versus bursty demand that comes about. To the customer, though, we would have to create software that can tolerate that eviction, right? Like you're going to get kicked out every once in a while when the compute is needed, and we'll have to figure out how to make that smooth transition.
That's really I think the theme behind the webcast is really this whole world of tech economics.
Right.
And the world of tech economics has really come out of the cloud and hyperscaler environments in which you had so many of these economically interesting problems, pricing, utilization management, ad placement, and all these tremendously interesting under the hood. There are fundamental economic problems about how to design and build efficient markets. So it's interesting to go from that very macro thought to zoom already in all the way into here's actually a very big, very significant use case where we're seeing it in action in the EDA world.
Yeah, for sure. And it's growing. I mean, there's so much interest, and actually in the land of AI, there's actually even more interest as to how to use cloud to accelerate your chip design or improve your chip design, right?
Yeah, maybe let's dive into that. Obviously, one thing, I run a large ASIC organization. We build hundreds of millions of devices every year, a couple of designs per year. As I think about how am I going to consume and how am I going to leverage AI and ML, obviously one way to do that is just wait for the tool vendors to build it in the tools. But where do you see as the other approaches? Like where should I be looking to leverage AI in my ASIC flows and my semiconductor processes?
So I think what I like to say is identify your biggest issues, right? So wherever you have the biggest issues, we could focus on those. And those issues may be common or they may be very unique to you or to Western Digital, right? And I think that's where folks spend their time developing custom AI models or custom AI approaches based on things that they need to do which may be different from others. And it's also an area of differentiation, right? I'll give you an example of one customer I talked to who's developing something pretty interesting. They're actually also looking at storage and hard drives and stuff like that. But what they were looking to do is, can they come up with a model which represents the behavior of a hard drive, right? A mechanical thing, right? So based on different temperatures and environmental conditions, and even maybe the pattern they're reading off the drive, is it possible to come up with a Gen AI model or some kind of model which represents that, given the fact that, one thing is they have enormous quantities of data, right? And so that was an area which we looked into. Is this something that can be done?
It's a digital twin of the drive.
It's a digital twin of the drive, right? And I think digital twins is an area actually where semicon folks are way ahead of much of the industry in digital twin creation. But this whole general area of can a model be used to be a digital twin of something, I think that's a burgeoning area, and it's going to be very unique to each customer, right, as to what they're looking for.
And I know, Adarsh, you've spent some time in this digital twin arena. What's happening in the industry level?
Yeah, I mean, I think as Ravi sort of rightly put, the semiconductor industry has been thinking a lot about it. The one area which I think has been a little bit of a challenge for the semiconductor industry is to be able to share data across different processes. Because the whole premise of having, let's say, a good digital twin of a drive would be that you're able to simulate all the way from the fab manufacturing to like the mechanical components to how much sort of shear there is in the motherboard, what have you, right? Like you should be able to do this end to end in the stack.
One of the issues that's top of mind, I think, for everybody in AI and compute and data centers around the globe is power.
Oh yes.
And I'm sure you're on the same industry circuit that I'm on.
Yeah,
industry circuit.
You're hearing the same concerns. Is there a role for? Obviously, there's a huge role for AWS, but is there a role for this technology to help with the power problem, the power challenges?
So I think, as you mentioned, I'm on the same industry circuit, and I think there's a lot of talk about the data centers that are being built today. I mean, you may recently heard that Meta just demolished one of their data centers because it couldn't handle the power, or is not designed for the power for AI, right? I hear that current racks are at 130 kilowatts roughly per rack, going to 250 kilowatts. When I think about that, I'm just thinking, that's just astounding. 250 kilowatts in a small, like 3x3x8 area or something like that. That's astounding. And we hear that literally power is going to be the limiting factor to building these data centers or to expanding AI capability even at a nation level even, right? And so what are the answers? Apparently nuclear is one of the answers, right?
We can get 3 Mile Island fired back up.
Well, apparently there's all this new technology in the nuclear space where you have these small form factor nuclear reactors. I think even in the US, there's a bunch of projects which are getting started in that area. In other parts of the world, for example, in China, I think there's a lot going on in that space. But power optimization is absolutely critical. And so, you definitely have, if you look at the startup landscape right now, especially on the AI side, the general thought is that pretty soon, if we're not there yet, is 90% of the AI workload is going to be inference, right? And so if you focus on that inferencing area, how can you reduce the power there if it's hard to do on the training side? Although I have some comments there too. But on the inferencing side, that's where there's a lot of focus being put into specific silicon to solve. This is this particular chip is good for this kind of architecture, for example, right? I actually recently met some companies who are able to do inferencing at the edge in under 5 watts, right? Which is pretty remarkable. So there's a lot being done there with the idea of reducing power and increasing throughput on specific, very targeted use cases, right? On the training side, you have the big GPUs, obviously, but then you have other folks who are also working in that training side. Amazon, for example, has their own silicon, Trainium, and Inferentia, which are high performance, better power performance, cost, all that stuff. But yeah, it's a big issue. And one of the ways to improve power consumption is reducing the time of training, for example. So what does that require? Better storage pipes, higher throughput, less I/O weight, better networking, all this kind of stuff.
Yeah, I think the important aspect here, maybe for our viewers and listeners, is that when you think about data center economics, it's like this multi-factor optimization. You have to have floor space, power, networking, and you kind of have to fit the largest possible productivity workload. I don't even want to call it compute because you could have storage as well there. Productivity workload in those constraints that you have. And, you could adjust the supply side, go to the 3 Mile Island, build your new power data center, or you could adjust the demand side. And I guess the demand side is where a lot of the industry participants are leaning towards.
And I think we're still in the the gold rush, wild West area where
that's right.
Look, you need shovels to dig gold. How much do shovels cost? Well, they're $500.
Yeah.
Okay, I'll take $1 million. Right. Whereas as the industry evolves, and particularly if we go after, I have a thesis that there's going to be a lot of we'll call it thin value in the long tail of enterprise AI. And much of what we see today is a battle for hyperscalers, model supremacy, going after those big social and search franchises. But if I think about everybody in the world extracting value, that more those thin value, right? I can write an email faster, I can write a doc faster, I can respond faster. That requires a highly optimized solution for inference and a highly optimized use. And so we're going to have to move from this sort of architectural free-for-all to really engineered systems that do these special purpose functions extraordinarily well and are extraordinarily efficient in power and storage and compute and everything else.
Again, great point. And we see a lot of this going on in EDA and chip development. Clearly NVIDIA is going to be a leader in developing models, right, for chip development and stuff like that. And I was recently reading a paper from them about ChipNeMo, which are the special models. They actually have BioNeMo, ChipNeMo, a lot of these NeMo type models for particular areas. And the concept is that if you do something called domain adaptive pre-training or very specific model development for a particular area, you can actually get those models down to be pretty small, right? Much smaller than the big general large language models. And if they're smaller, they're more efficient. They run on smaller hardware, take less power. yada, yada, yada.
Yeah, I mean, it's actually kind of very straightforward once you stare at the LLMs. It becomes obvious why this is the case, right? Like when you have a really large parameter model,
Right.
the same model is storing information about cooking recipe just as much as it is saving about whale hunting, right?
Right,
Like,
right.
and
Right.
maybe you combine the two, but maybe you don't in most use cases. And so the idea that if you can sort of have these general models becomes useful when you can't retrain the parameters, which is theta, but then you can retrain the inputs that you give to these models because it's an auto-regressive machine. Makes prompt engineering useful because with prompts you can extract value out of it.
Right.
But then if you know that your domain is going to be very constrained, you straight up go to a more condensed version of the model. And I'm sure if you take an EDA foundational model. I can't answer questions about podcast from it, right? Like, but it's still a very useful value prop, and you can infer things much faster.
Yeah, absolutely. And I think that seems to be the trend, especially in these very specialized areas, right? I'm sure it'll be similar in medicine, it'll be similar in finance, that you wind up with these very specific models, right? And so then at the end of the day, what I think, it's just thinking out loud, is that you will have a lot of these models for very specific skills or very specific domains, and they'll be orchestrated by some larger model, right? And so that's the concept of agentic AI, right? Where you have a large model saying, okay, you go off and do like assertion testing, you go off and do like floor planning, you go off and do design rule checking or whatever, right? And so there'll be lots of these little models being orchestrated by a big thing to ultimately give you a result.
Yeah, I mean, going back to our topic here of just how is ASIC development itself, you can see a lot of the work that's going on today is at those leaf nodes.
Right. Right.
It's at that floor planner. It's at a accelerating logic design or compilation. Clearly now, can we start to assemble those leaf nodes and do more interesting constructs?
Yeah, when I was sort of growing up, a lot of the evolutionary computing would have super interesting answers to even these leaf nodes, right? Like if you ask the computer, hey, you have a genetic algorithm by which you have to kind of come up with a floor plan, it'll do organic stuff, things that we wouldn't do as human beings. Perhaps not good for fabs, but at least cool, right? Like, and it'll be interesting to see now that once you create those toolkits, which are a little bit of an expert system, or things that have rigidity, but then overlay this fluidity on top of it, what the system can come about in terms of a chip design, or even some form of new memory.
Absolutely, and I think I saw bits of this. Several years ago now with ANSYS, right? Who's working heavily in mechanical design and mechanical CAD and stuff like that. And they came up with this concept of organic design, where the tools, the AIs would come up with designs that had huge holes in them, right? And it actually harkens back to some work it made me very think about some work I did when I was doing my PhD. I wrote this piece of software which was essentially like a finite element modeler of current flow through any arbitrary structure. Mm-hmm. And essentially what I remember seeing that, current stays pretty much constrained to particular areas to the point where there's a lot of metal in wires, which seems to be redundant. You don't need this metal, right? And I think that's what the tool did too on the design of a chair or a piece.
Great scale, right?
Right, exactly. Right. Because, if all the weight distribution or whatever they look at goes down certain channels, then why have material in places where nothing's really happening?
Yeah, well, we talked on our security topic, we talked about this, is the notion of, is the AI trying to reproduce a human way of thinking and human way of operating, or are we trying to get the AI to do something a person could never do or would never do?
Yeah, exactly. And I think that's part of the challenge and part of the amazing thing which AI can do is because generally you give the AI problems constrained by the way we think, right? And so it's not as free-flowing as perhaps, or in many cases it may not be as free-flowing to come up with a very unique answer because of the way we've constrained it. And so I think that's an area of a lot of interest. What if you let this thing loose? What could it do? Right?
So we're talking a lot here about that AI, about the ASIC design phase. Of course, there's a process design phase that's happening on the left side of this picture, where the fundamental process being developed. And then there's this huge manufacturing operation that's happening on the called the downstream side, where these are being produced. Of course, at Western Digital, we have, with our joint venture with Kioxia, one of the largest semiconductor makers in the world. And I can say, those are unbelievably data-rich problems. Their problems are extremely well-suited to both conventional AI, ML, as well as advanced AI algorithms, because they are problems that humans have an extraordinarily difficult time with, which is, how do I optimize 100,000 test vectors? How do I take this mass amount of data streaming off my fabrication and production and quality management processes, and how do I use that data? So I think we're just scratching the surface at the full value chain extraction of both big data and AI ML.
And these operations are so massive that even 1-2% gains here and there accrue a lot, right? And you can sort of put it in dollar terms.
No, it's an enormous impact.
Yeah, no question. And you're absolutely right. It's the volumes of data that are almost debilitating for a human mind to comprehend. And I think it's great for a model, right? So that's exactly what they need to find those patterns, to see those optimizations. And it's early days, as you said, right? But the opportunity is enormous to figure out these
going
things.
back to your previous constraint comment, a lot of that is not set up for generative AI today, right?
Yeah.
They are streams of data that come in a very raw format, or sometimes in telemetry format and whatnot. So you do need to have that layer that sits in between that raw stream of data and something that can orchestrate and extract value out of it.
Yeah, I agree. And I think that's where there's a lot of uniqueness, going back to what you said about should we mainly be focusing on looking at tools, at AI capability in the commercial tools, or doing our own, right, or building your own? And this is one of those areas where building your own can unlock enormous value.
So does AWS sort of use AWS to design Inferentia and Trainium on the cloud?
Absolutely, yeah. All of Amazon design is done in Amazon, all of Amazon chip design, right? So, and also using the gamut of all of our EC2 instances and different storage options, including our ARM-based instances, right? So that's another interesting thing we have from a power and performance standpoint, is that if you use ARM-based CPUs, they can be quite more power efficient than the standard x86. And so that also is an area where there's a lot of interest overall in using those CPUs, because it can help you with your ESG requirements, for example, right?
So I want to come back to this core. How do we enable more semiconductor services to migrate to the cloud? What's the best way for people to learn about this, or kind of get up to speed? If I'm a director of CAD engineering, how do I ramp up on this technology?
One good place is YouTube, right? So there's a lot of YouTube videos, even by a lot of Amazon folks, or past reInvent talks, which talk about, what others have done, right, and how it's worked for them. So that's a great place to start. If my contact info is on this podcast, reach out to me directly.
I'm sure we can find you, yes.
Yeah. I'm happy to talk about what we can do and what we can offer. And also, if you just go to a search engine and type in AWS Semiconductor, it'll take you to our main page where you can learn about what we're doing. I even wrote a TCO blog about economics of moving to the cloud for EDA workloads, which is pretty popular, actually.
An actual TCO where I can look to build my own model for the ROI. Excellent.
Yes,
Excellent.
Yes.
Well, Ravi, thank you so much for joining us. It's been a super entertaining conversation.
Thank you.
Come back anytime you'd like.
It's been awesome. Thanks for having me.
Thank you for joining us for today's episode. If you enjoyed it, like, share, and subscribe. And we're always looking forward to hearing your feedback. And be on the lookout for the next episode of Silicon Economics.